Today we are going to learn on the topic which is interference by the division of amplitude. In our previous class we have discussed the interference due to the division of wavefront. Let us first begin with the Stokes treatment on the phase change due to the reflection. Here the picture shows two different media, one of refractive index N1 and other of refractive index N2, and the interface is showing over here. A ray of light with amplitude A is incident on the interface and it gets reflected and as well as transmitted or refracted. Here the R and the T are the reflection and the transmission coefficients, which means the fraction of the amplitude which gets reflected is called reflection coefficient, and the fraction of the incident amplitude incident ray is called which is transmitted is called the transmission coefficient. So AR1 and AT1 are the new amplitudes and new amplitudes for reflected and the transmitted rays. Now due to the principle of reversibility of light, we can again simulate this situation by reversing the direction of the light. So we incident light of AR1 amplitude and which gets reflected by an amount of AR1 into R1, that means R1 AR1 square, and transmitted which has the amplitude of AT1 AR1 into T1, this one. Okay, and similarly another incident light in the reverse direction AT1 is incident on the interface and gets reflected by an amount of AT1 into R2. Why R2? Because the light is going from N2 medium to N1, that is why the reflection coefficient is reversed, is different, that is R2, and another part gets refracted into the medium 1, which is AT1 into T2. Because the light is going from N2 to N1 medium, the reflection and transmission coefficients are different from the previous case. So T1, R2 and T2 are here. Now due to the principle of reversibility of light, you should get this phenomena. That means number one light gets divided into two parts, 1 and 2. Say this light is divided into two parts. The first part is this and the second part is this. By the principle of reversibility of light, if I incident the 1 and 2 light, then it will be joined and give rise to the primarily incident light. Okay, so this light should vanish. That means AT1 R2 plus AR1 T1 should vanish. So it is written over here, there. So from here you can formulate that R1 is equal to minus of R2 or R2 is equal to minus of R1. Here it is written according to Stokes, R2 is equal to minus of R1. He had taken this. So R1 into e to the power j pi can be written here. Okay, because e to the power j pi, use the de Moivre theorem, you will get minus 1. So e to the power j pi signifies the phase difference between R1 and R2, which is pi. Okay, this is the phase part. So pi phase difference happened due to the reflection from the rays which are coming from 1 to 2 or 2 to 1. So Stokes states that to unify this theory, Stokes states that the light which is reflected by a medium, by an interface backed by a denser medium, has extra pi of phase difference. Okay, so this is the theorem of Stokes, which will be used in our this class. In this lecture we will use this. The first topic is the interference in thin films. Here I have taken a parallel film. Okay, parallel thin film. That means soap bubbles can be think of, or oil film. Those are the examples of thin film. I will show you in the last section of my class what is the physical use of the thin film. The Newton's ring experiment I will show you, but for the time being you can think of anything. You can think of a layer of oil on the surface of the road, or a soap bubble. You can those things are can be treated as thin films. So let us take a thin film where the upper surface and the lower surface are parallel to each other, and the thickness of the film is d. Light is incident at an angle I and gets refracted by an angle r, and it is again reflected with an angle r, and which is finally transmitted, number 2, to the vacuum, and the first part of the incident light gets reflected from the top surface, which is denoted as 1. So 1 and 2 lights are coming from the same source. The source is here. The source is here. Okay. So same source produces 2 lights, 1 and 2. One light is just the reflection from the top surface, and the second light coming from the reflection from the bottom surface. So due to the reflection at this point A, there should be a pi extra phase difference, extra phase change of the reflected light than the incident light, because of the Stokes theorem we have just discussed. Now let us calculate the condition for maxima and minima, because 1 and 2 lights are coherent lights because they are coming from the same source, but their amplitudes are different. The amplitudes of 1 is higher than the amplitude of 2, as due to the successive reflection. It is said the amplitude is A here, so AR1 is the amplitude of light 1, but the amplitude of light 2, what is that? AR1 into T1. This light is CD light is AR1 into T1 into R2, and this one is AR1 into T1 into T2. So the amplitude part is very much different. We have to study this different phenomena, that is interference due to the division of amplitude. The amplitudes are different and gets reduced as you go further. Okay, so let us first calculate the path difference between 1 and 2 lights. The path difference, for this there is a normal drawn on the AB light, which is BD or DB, you can say. The angles are deduced using the simple trigonometry. You can do it by your own. And the path difference, what is the path difference? The path, here you can see the path is same after the point B and after the point D. The length of the path of 1 and 2 are same because they are traveling in the same medium with same speed, that is the speed of light. So the paths will be equal. But previously in the back of these points, AB is the path traveled by the light 1, but the light 2 traveled AC and CD path, which is very much different from AB. So there is a path difference. Actually the path traveled by the light 2 before the point D is mu into AC plus mu into CD, where mu is the refractive index of the material of the thin film. Okay, so mu into AC plus mu into CD minus AB is the path difference. Now use the geometry, simple calculations. AC can be deduced from this triangle, which is d by cos r. Here CD is also d by cos r. So twice d by cos r are the lengths of AC or CD. By multiplying mu, 2 mu d by cos r minus AB is there. Now AB, how you can measure AB? AB is again in terms of AD, you can write it. See, it is done here. AB is equal to AD into sin I. Okay, and again in place of AD, you can put twice of AE. So twice of AE into sin I. Now what is AE? AE you can derive from here, from the triangle ACE, that AE is equal to D into tan R. So all things are put together, and now use the Snell's law, where sin I by sin R is equal to mu. So sin I is equal to mu into sin R. So this will generate this term, and now just doing some simple calculation, you will reach to this point 2 mu d cos r. Now mu is equal to 1 in case of air film. If you assume the film is made up of air and outside there is a different medium, for soap bubble it happened, so the mu will be vanished from the calculation, but that is a special case. So 2d cos r is written over here, but I am keeping the mu term. Now the interesting thing is what I have told earlier, that there is an extra path difference, phase difference of the light AB at the point pi due to the Stokes law. So phase difference pi will generate a path difference of lambda by 2, because pi phase difference means 2 pi by lambda into pi is equal to lambda by 2. The phase difference is the path difference is lambda by 2. Now the extra path difference should be added to this term, so the net optical path difference will be 2 mu d cos r plus n by 2. As we know that if the optical path difference is n lambda, then the maxima condition, that is bright fringes, will appear. From here you can see that 2 mu d cos r is equal to twice n minus 1 into lambda by 2, where n is equal to 1, 2, 3, not 0. So this is the condition for max. It is it seems that the condition gets just reverted than we have studied in case of division of wavefront, but don't think so, because the condition for maxima and minima are the same. The formula looks just opposite to what we have got, is just because of the fact that extra path difference lambda by 2 is there. So it added extra number to the n lambda, so the even term gets into the odd one, and odd gets into the even. So that is an interesting feature which generated over here. And the next topic is again the interference condition we are going to evaluate, but with the transmitted light. It may so happen that your telescope is, if your telescope is put at this medium, at the top surface, over the top surface, then you will observe this kind of feature, but your telescope is focused at the lower part of the film, then you will get the complementary condition for max and min, which means proceeding in the same way, just calculate the path differences between two rays, the one which is transmitted from this light, and the second one transmitted from the reflected light. So T and U are your two interfering waves here, but with different amplitude surely, and the geometry takes different form, but I and R are there, and the calculation is some weight is longer, but very much doable and very much easy to understand if you understand trigonometry. Then you can reduce the path difference. One thing you should remember here, see, the path difference formula becomes similar again, 2 mu d cos r, but there is no extra phase difference at any point, because you are focusing on the interfering waves which are transmitted. No, so reflected waves, we are forgetting about the reflecting waves. So the transmitted waves are of our concern. So the transmitted waves are not Stokes reflected, that is no extra path difference is there. So this is the path difference between the two rays, interfering rays, as well as this is the optical path difference between two rays. Okay, so here the condition for max and minima are just similar to what we have got in case of the Young's experiment or so. Now let us put our hand into some calculation which is very much general, the wedge shaped film, where the top surface and the bottom surface are not parallel to each other, making an angle alpha to each other, and the geometry is some more is complicated than the previous case. Now let us first understand the geometry of the interfering waves. Now the incident wave is AB, the reflected wave is BR, and the transmitted wave is BC, which is again reflected by the lower surface CD, and then it is transmitted DR1. Then they will interfere to some region. You will use the lens to focus them, to interfere them into your field of vision. So we are going to study the interference pattern have originated from BR and DR1. So they have path differences which are that is the mu into BC plus mu into CD minus BF, that is the path difference. It is written over here. And now CD can be using you use the geometry. Okay, this is the angle alpha. Okay, so one can prove this angle is also alpha, this angle is R plus alpha. Okay, just draw some perpendicular and do some trigonometric basic formula from your class 9-10, that is the opposite angle, similar angle, corresponding angle. You will reach this point, that this angle is alpha plus r, this angle is alpha plus r, this angle is alpha plus r. These are the important triangles. So let us focus on that. So r plus alpha, now this is r plus alpha, this is r plus alpha. So this is the triangle where the two sides are equal to each other. So CD is equal to CP, as well as this side and this side also are equal. So CD, in place of CD we can write CP. No, it is not written here. The BC gets divided into two parts. Okay, let us study BC. Okay, BC is here. BC can be divided into two parts, BE and EC. Okay, so EC plus CD, CD means CP. So EC plus CP will give you EP. It is written here. Okay, yes, it is EP, and mu is multiplied with that, and another term will be cancelled to each other, because BF is equal to mu into B, so mu B cancelled. Why? Because the calculation is given here. Sin I is equal to BF by BD. Okay, sin I is equal to BF by BD. Where is BF? BF is here. BF by BD, and sin R is equal to your BE by BD. Sin R is equal to BE by BD, because this is R, this is 90 minus R, so this angle is again R. So angle BDE is your angle R. So BE is perpendicular by and BD is the hypotenuse. So BE by BD is sin R. So take the ratio of them, it will give you mu, and mu is equal to certainly BF by BE. So Bf is equal to mu into B. So mu B cancels each other, so mu into EC plus CD will be there, and EC plus CD, and CD is equal to CP. So EC plus CP is equal to directly EP we can write. It is written over here, and EP from this triangle you can evaluate. Consider the triangle EPD. It is a right angle triangle with right angle at angle DEP. So this is the base and this is the angle R plus alpha. So EP by hypotenuse, which is DP, is equal to cos of R plus alpha. So EP is equal to DP into cos of R plus alpha. And what is DP? DP is equal to the twice of this length. This length is assumed D. Here in the previous case, the two surfaces are parallel to each other, so the thickness is uniform all over the surface. But here at the point D, the thickness is small d. That is our point of investigation. At our point of investigation, the thickness of the film is D. It is variable at every point of the top surface. Okay. So D is the small d, in terms of small d it is written, and for the same reason as we have discussed the Stokes theorem, the extra path difference lambda by 2 is introduced at the point B, because this is the interface which is backed by a denser medium. Mu is greater than the air, the medium within the film is denser than the outside medium. So at the point B you get the Stokes reflected ray, that is BR. For this, lambda by 2 path difference is extra added to the optical path difference. So this is your mu optical path difference, which should be is equal to n lambda for constructive or interference or maxima condition, and the formula will be look like this, and for minima the condition will be reversed for nth maxima. And for very simpler case, we can find here the fringe width. Okay, we can find fringe width by taking some assumption, that is we are dealing with the those rays which are incident normally on the surface. Okay, from here the assumption begins. So if the ray fall on the surface, fall at B via the normal, then R will be 0. So the formula will be simpler with R is equal to 0, and also assume that mu is equal to 1. That is, the thin film is made up of air, and the outside medium there is another medium. So mu is equal to 1 there. So let us consider this simple figure at the point of investigation where the thickness is D and there is alpha, and the distance of the nth fringe at the point of investigation from the edge, from the vertex or from the apex of the thin film is xn. Okay, that is the distance of the fringe, whatever it is, max or mean, from the end point of the wedge shaped film is xn. We have to first find out xn, then we will evaluate xn plus 1, then we will subtract xn plus 1, xn from xn plus 1, which will give you the fringe width. Okay, so xn, how we will get the xn? Using this triangle, simple triangle, using the tan formula you will get. Here the calculation is done over here. It is very much simple. D can be found from this expression, can be put here. So xn is this. Now xn plus 1 is this. Put in n plus 1 in place of n. So it will give you this, and just subtract them. Xn plus 1 minus xn will give you lambda by 2 sin alpha, which is the fringe spacing, that is the fringe width. It is done for the maxima condition, that is the bright fringes. Do by your own using the minima condition written over here. You will reach to the same point, that is lambda by sin alpha. If alpha is very much within 4 degree and measured in radian, then sin alpha is nearly equal to alpha, which is a practical case, because in our thin film cases The thin film, you can see the thickness of the film, that is a soap film on your tabletop. You can see by your naked eye what is the thickness. So the angle of the wedge is very much small, that is alpha is very much small. So the assumption is nearly true for every cases. Lambda by 2 alpha is the fringe width in this present case. Okay, these fringes are called fringes of equal thickness. Why? Just look at the formula, you will get the result automatically, because if your d mu is constant, r is constant for a particular ray, alpha is constant, so left hand side all are constant except d. In the right hand side, n is a particular order and lambda is constant for our monochromatic light, which we have used here. So n is the variable thing. So d and n are proportional to each other. So if you increase the d, then n automatically will increase for a particular ray, for a particular wavelength of light. Okay, so thickness will determine the order of the fringes. So these fringes are called fringes of equal thickness. If you don't vary the thickness d, then you will get the same in the same order at that point, whatever it is, max or mean, but the order will be the same. See the 3D picture here. The BB prime, this is a line which is at the same height from the bottom surface of the film. So D is equal at every point between B and B prime straight line. So every point will satisfy the same max or mean condition with same order number n. So we will get the straight line fringe at the top of the surface. So we will get straight line fringes which are parallel to the top surface, and alternately bright and dark we will get, and those fringes are called fringes of equal thickness, that is named after also called Fizeau fringes. This is very important thing, because we will show another another fringes which happened due to the interference, but not fringes of equal thickness. So I will come later in my talk. Now the topic is colors of the thin films, which is similar as we have talked, that at the very end point of the film the thickness is 0. So put 0 here. So just put 0 at the condition. What is 0? If you put 0 at the expression for path difference, the path difference should be lambda by 2. Lambda by 2 path difference means the phase difference is pi. So destructive interference will happen there, because lambda by 2 means the destructive interference condition satisfied. Okay, don't mix up with this formula. There is 2 mu d. No, this is coming after calculations where lambda by 2 is taken to the right side and then manipulate it. Then you will get the these formulas, these two formula originated from here. Sorry. Okay, just look at the basic path difference formula. If d is equal to 0, path difference lambda by 2. Path difference is lambda by 2 means 1 into lambda by 2. So 1 into lambda by 2 means the interference minima condition. Okay, so minima condition is satisfied at the end point. That means dark fringe will appear. Then with the height increases, the alternately bright and dark fringes will appear along the top inclined surface. But if you use the white light, then the every color will satisfy the minimum condition at the end point, because it is independent upon the wavelength, it is independent upon the thickness, and thickness is 0 there. But after that, when thickness get increases, then depending upon the value of lambda, the some point there will be max for red and mean for violet will be there. So colored fringes will appear. We can say by just summarizing this concept, that colored fringes will be appear, because at every point some rays will give you the max and some other rays will give you the mean, and but at the very end point the all colors will satisfy the dark fringe, that is the minimum condition will satisfied by the all colors. Now let us move on the experimental verification of the thin wedge shaped film, and the use to and we will use this experiment to measure the wavelength of unknown light, unknown monochromatic light. This method is known as Newton's string method, and here also fringes of equal thickness, because the film is produced between the plano-convex lens and the glass plate. Okay, the air film has been produced, so mu is equal to 1 in our case. And the experimental setup is given over here, the source at point S, and the parallel beam of monochromatic light is incident on this, and then this mirror will reflect the rays coming from the source, and then it will be reflected back to your microscope, and they will interfere, that reflected rays will interfere. Let us take a microscopic point of view of this picture. Let us take one ray AB, which is incident, then refracted, then reflected from the lower surface of the plano-convex lens, and which is again transmitted and then again reflected and again transmitted. Now the two rays 1 and 2 will interfere to give you the interference fringes, because they are coming from the same sources but with less but different amplitudes to each other. So this is the phenomena of division of amplitude, and also the division of amplitude interference pattern will be observed here, but from the wedge shaped film, because see there is a wedge shaped film here. Now just jump into the direct calculation. Here also there is an extra path difference because of the interference at this because of the reflection at the point D, because that point D there is a surface backed by a denser medium. Okay, so the path difference is 2 mu d cos r into a plus lambda by 2. It is the total path difference between the rays 1 and 2, but here mu is equal to 1 and r is nearly equal to 0, and wedge angle alpha is taken 0 also for the sake of the simplicity of the calculation. Okay, if you done this by your experiment, then you will know this. You know this very well, that the wedge shape is very much small, cannot be viewed by our naked eye, and it is very much lesser angle, less than 4 degree for sure. So I will drop it. So alpha is gone and r is nearly equal to 0 for the normal incidence of the light, which is our experimental condition, that is normal incident of light is happening over here. So r is equal to 0. Now if r is equal to 0 and mu is equal to 1 and alpha is equal to 0, you will get the simple form of the path difference, which is 2d plus lambda by 2. For the calculation of bright fringe, the path difference should be n lambda due to the interference max condition. So 2d is equal to 2n minus 1 into lambda by 2, and for the dark fringes you will get this formula. Now d, we will put the d, because d is very much difficult to calculate, because d is what? D is this distance the thickness of the film at the point of investigation. Okay, so let us consider this picture where the plano-convex lens is there and the total sphere of the lens is constructed, imaginary sphere, where the C is the center of curvature of the surface, A low L prime, and D is the thickness of the point of investigation. So D cannot be measured practically. See, so D can be replaced by things which can be measured practically. So for this, let us consider this triangle COP, this triangle. This is not triangle actually, but okay, we can assume that because the alpha is very much small. So this can be OP, can be the arc length OP can be treated as a straight line. So D is there, so NO distance is D. So using similarity triangle, we can write that NP into NQ. What is NP? NP into NQ, this one, is equal to NO into ND. That means NO into ND. ND, where is ND? Yes, this one. That is the property of the circle. The length of the chord is divided into two parts by the diameter. So the each part chords, the length of the each part of the chords, the product of those, that is NP into NQ, is equal to the product of these two lines, NO into ND. This can be proved using trigonometry also. You can use different technique to prove this. Now put the values R, which is the chord length NP of this circle. The chord length is R. R is also the distance of the fringe from the end point of the wedge. Okay, so R is very much important to us. So R is the length of the fringe. I am telling the length, but I will come to this point later. Let us first calculate this R. So R, this is also R, so R square is there in the left hand side, and NO and ND can be evaluated D and 2R minus D, where R, capital R, is the radius of curvature of the lens. So CO is capital R. So simply OD means nothing but twice of R. So NO is twice of R minus, sorry, NO is D. So ND is twice of R minus D. Okay. So this has been put here. And see, there is an approximation. D is very much small, so D square can be neglected. So twice RD is equal to R square. So R is equal to root under of twice. So okay, D is equal to R square by 2R. Now we put the value of D into the equation for max condition here. You can put over here D is replaced by this expression R square by 2R will give you this equation. From here R can be deduced. So R, what is R? Now let us take this picture, look at this picture in a different way. R is the distance. I have told you that R is the distance of the fringe happened at this point from the wedge, from the end point. But here the fringes are of equal thickness. Why? Because the fringes are of are produced from the wedge shaped film, and here D is constant, where whenever at those points where the thickness of the film are constant, those will satisfy the same interference condition, whether the max or mean of same order n. So you can see there the points, the locus of those points having same thickness, having residing at the same height from the top surface of the plane's glass plate AB, that is the D, the points residing at the height D are so many. two points are showing here, one P and another is Q, but there are infinite number of points, as because this lens is a plano-convex lens, and there is a circle with radius r, which has infinite point at its periphery, and those infinite number of points on the circle are at same height d from the surface AB. Okay, so those points, that is the circle of radius small r, will satisfy the same identical max or min condition. So nth max will be a circular ring of radius r. So the fringes will appear, as you see from here, from the top of the plano-convex lens, you will see some rings. That is why the Newton's ring experiment it is called. So the ring radius you have evaluated in due course, and you can find out the ring diameter also. Dn is twice of r. So in place of r you can put d square by 4, and there you can simulate that dn is equal to root under of 2 lambda r into root under of twice n minus 1 for the nth bright fringe. For nth dark fringe, the formula will be dn is equal to 2 into root under of n lambda r. Whatever you want you can use. Now what is dn square? Using the dark fringe, nth dark circle we are interested because the formula is simpler. So dn square is equal to 4n lambda r. So if we move our crosswire of the telescope by p dark fringes, that is, after the p number of circles we focus our crosswire, that is, we shift the pattern by n plus p order. So now the diameter of the ring will be dn plus p, and the formula here just put n plus p in place of n, so it will give you this. So just subtract dn plus p square and dn square, it will give you 4p r lambda. So lambda is equal to dn plus p square minus dn square by 4p r. P is the shift of the fringes, that is the shift of the number of the dark fringe, and it will be experimentally very easily calculated. And r is the radius of curvature of the plano-convex lens, can be measured by a spherometer, and these are the diameter of this ring, can be measured by a travelling microscope. So lambda can be find out using this formula. Conversely, you can if lambda is known, you can find the refractive index of unknown liquid. How? Let us put the liquid into this gap. So let us suppose an oil which you don't know the refractive index of the oil. Just put in this setup the oil. So oil will fill this gap, this air gap. So now the thin film is made up of not air by an oil. So mu will be there. In our first case 2d is written over here, but now 2 mu d should be written. So mu will be multiplied with d. So d will be accompanied by a mu. Okay. So d is accompanied by mu. So the diameter will be accompanied by 1 by mu. Because proceeding in the same way, you can calculate that mu will appear the denominator of this formula, r square as well as d square. So this is our calculation for the air film. First, calculate for the air film. Shift the p number of fringes, say p number of dark fringes, dark circles, and you will get dn plus p square minus dn square is equal to 4p lambda r. Okay, now spread the oil over the surface of the glass plate, then the same result but with mu by division, by dividing mu will be appeared here, and also the rings will be different in dimension. So b prime are written over here. Just divide these two equations. Now it will give you mu is equal to, this is happened into the air, and travelling microscope will calculate the d's, all d's can be calculated. Now one thing you should keep constant, which is the number of dark fringes which are shifted, that is the p, number p, because p is cancelled over here. So p is kept constant here. So mu can be determined by this formula. This is another case which is called the fringes of equal inclination. So far we have talked about the fringes of equal thickness. What is the fringes of equal inclination, which is called Heidinger fringe? Let us consider an extended source, a long source, and the light from the source fall on the parallel thin film. Okay, parallel thin film of thickness t. To make our calculation very easy, we are taking the parallel film, and here consider 3 point sources where in every direction light will come out, but we are considering those lights coming from 3 points S1, S2 and S3 of the extended source, which are incident on the top surface by an angle theta. Incident angle is theta, so the reflecting angle is theta prime, say. So the condition for the optical path difference is 2nt into cos theta prime. Why n? N is the refractive index. Okay, so theta prime is the internal angle, and by the same technique you can find out the theta prime, the optical path difference, which I have talked earlier. 2nt into cos theta prime is equal to m lambda if the dark fringes appear. Here the condition, due to the Stokes theorem, the condition gets reversed, and the condition for dark fringe is m lambda. So m is the mth order of dark fringe has been taken over here, and cos theta prime is equal to m lambda by 20. You can here the theta, cos theta prime, not theta, cos theta prime. Now cos theta prime and theta are proportional to each other because of the Snell's law. So cos theta prime is equal to m lambda by 20. Now for a monochromatic light, lambda is constant, n is the refractive index of the film is constant, t is the thickness of the parallel film is constant. So m and theta prime are related to each other. So if you change m, then it will changes theta prime, and theta prime will change obviously the angle theta, that is this set of rays will be changed. So for this set of rays which are incident at an angle theta on the surface will satisfy the same interference fringe which is produced by this lens at the your point of your field of vision. So the interference will be will produce some fringes which are fringes of equal inclination. Okay, so this is called Heidinger fringe also. Now the problems you can solve, there are so many problems given over here, do by your own. At this point, let us thank you for listening.